the false positive paradox, and the fallacy of base rate neglect. So you just got your coronavirus COVID-19 test result and it's positive. How worried should you be? Well, maybe not as much as you think. Stay tuned. Hello there. Imagine for a moment that you just received a positive test result for COVID-19, actually for the virus SARS-CoV-2 that causes COVID-19. When you're thinking, oh my, I wonder, is there a chance that it's wrong? Could it be a false positive? And the answer is, yeah, it's possible, but is it rare? Is it frequent? How often does this happen? Well, I won't make you wait to the end of the video to find out. I'll tell you right now that if we make some reasonable assumptions about the accuracy of the tests for COVID-19, and if we know something about the prevalence of the virus in the population, we can actually show mathematically that the probability that a positive test came from an uninfected person can be very high. Generally speaking, I would say throughout the pandemic, probably more than 50%. So stay with me. Let's take a look. Okay, to begin with, check out these two words, sensitivity and specificity. For any test that is meant to rule out or rule in the presence of a virus or a bacteria or some medical condition, these tests always have these two characteristics. The sensitivity of the test is the percentage of infected people, I'm using the case of the virus, who will test positive. Now, we want that to be high. I've set it here to 100% just as an example, which would mean that of 100 infected people, all 100 will test positive, 100%. The flip side of that is the test specificity. This is the percentage of uninfected people who will test negative. And we want that to be high as well, as high as possible, because if you are uninfected, you want to get a negative test result. And if you do get a positive result, that's called a false positive. So at a 98% specificity, that would imply a 2% chance that if you are not infected with the virus, that you will test positive. 2 out of 100 people will test positive who are uninfected, but the 98 others will test negative. All right. I hope that made sense, and I'm going to actually give you a little quiz right now. I should tell you that I am a long-time, 43-year community college mathematics teacher in California. I just retired recently. So I have to give you a quiz because it's in my blood. So here's your quiz. Suppose the PCR test for SARS-CoV-2 is 100% sensitive and 98% specific. If you test positive, what are your chances that you do not have the virus? Okay, why don't you think about that for a moment? You might want to pause the video so you can give it some more thought. I'll be here when you come back. Okay, I'm back. Are you back? All right, let's take a look. Before I reveal the answer, I would like to say I'm guessing that many of you have guessed B, 2%. And I'm thinking you're probably saying, well, look, it says up here that when the specificity is 98%, then if you're not infected, there's a 2% chance of getting a positive test result. And that's correct. But that wasn't quite the question. So here's the question you answered. If you answered 2%, you answered the question, if you do not have the virus, then what are the chances you test positive? Which is exactly what this says up here. But the question I asked wasn't the same. I said, if you test positive, then what are the chances you do not have the virus? You might be thinking, well, that's the same question. Well, it's not really the same question, and I have a quick little story I can tell you that I think will demonstrate that it's just turning the question around. It's known as the converse of the question, isn't the same. So, for example, I have a friend, Andrew, and Andrew gets up every Monday morning. First thing he does is he goes to Costco and tanks up. He gets a full tank of gas, and then he goes off to work. And the question I'm going to ask you is, so if And assume that that's the case in all cases. Every Monday morning he gets a full tank. So here's the question. If it's Monday morning, what are the chances that Andrew tanks up? And the answer is 100% because I just told you so. I said every Monday morning he does that. No exceptions. But what if I turn the question around and said, if he tanks up, then what are the chances that it's a Monday? Well, you might be inclined to say, well, I'd say it's a Monday, or pretty probably a Monday, or yeah. But actually, what I didn't tell you is that Andrew does this every single morning of the week, including the weekends. Well, I'm making it up, but it's so he tanks up every single day of the week. So if you know he tanks up, it tells you nothing about the day of the week. So the two questions are in fact different, and I hope that made sense. Well, let me reveal the correct answer, and that is none of the above. You might have guessed that because of my remarks at the beginning. So let's go to the calculation because this is where it gets really, really interesting. So I've added a third line here called the virus prevalence. That's defined as the percentage of the population infected with the virus at the time of testing. We need to know that, and in order to find that, we're going to actually, before we go ahead and do that, let's go back to sensitivity and specificity for just a second, because I'd like to come up with an actual test so we know what the sensitivity and specificity are for that test. And I found in this article from the Center for Health Security.org a list of literally hundreds of tests for SARS-CoV-2, their PCR tests, lateral flow tests, rapid antigen tests, and they all have a specificity and a sensitivity. And what I did is I downloaded it. They had a link to download it, and I put that into our spreadsheet under List of Tests. I also sorted it by specificity, so the lowest specificity first, and you can see as I move down, the specificity increases. There are tests, in fact, which claim 100% specificity, and if you can get a test, that's what you want, because if you say no, I want to wait for a test that has 100% specificity, that would be in your favor, because then you know that there are no false positives in that case. But what I think I'll do is choose a test which is kind of in the middle range here. How about this one, number 24? It has a 93.3% sensitivity and a 99% specificity, implying only a 1% false positive rate. Okay, let's take that information back to our spreadsheet. So the sensitivity of that test was 93.3% and the specificity was 99%. Now all we need is the virus prevalence. Well, it depends. It changes. It's seasonal. You know that during the summer months, the virus is not as prevalent as it is during winter months. Let's take a look at the Johns Hopkins dashboard. Actually, let me go back to what the dashboard looks like. So if you go to, well, I'll link to this as well. You can click on US, make sure that that's got a blue bar there, because otherwise it'll be looking at somebody else, some other country. So in the US, if we go over to this chart, it tells us what the weekly case rate was. So weekly number of cases, I should say. So let me open that up. And we can see that we peaked on January 16th. This is undoubtedly the Omicron variant. Tremendous prevalence of that variant, more so than at any other time during the pandemic. So let's take that. Let's see what happens. That shows 5.614 million cases in the week ending January 16th. Now, a case, how do we define a case? Well, the CDC has defined the case as a positive test result. Well, all right, but I'm saying in this video that many of those positive results are really in uninfected people. So the chances are excellent that the virus was not present in many, many, many of those 5.614 million people. But let's just use that anyway. So 5.614 million divided by 334 million people in the United States will give us the estimate for the virus prevalence, and probably an overestimate. I did that calculation, and it comes out 1.7, is that right? 1.7%. So let's go back to the spreadsheet and plug in 1.7%. And now we can see, I'll explain the magic in the middle in a few minutes, but we can see that the probability of not being infected, even though you tested positive, is 38.3%. Wow. I mean, that's almost about for every 5 people who tested positive, 2 out of those 5 were not infected. Wow. Okay. I'll explain, I promise, but let's take a look at maybe 2 more data points. So going back to our cases, weekly cases, let's take the last peak. Now, in the last wave, looks like it peaked here September 5th. There were 1.159 million cases in the week ending September 5th. And if you divide that by the population of the United States, and I did that already, it came out to be 0.35% of the population. So we'll go back, we'll plug in 0.35, and now, oh my gosh, look at this. 75%, that is 3 out of every 4 people who tested positive didn't have the virus. Is that really possible? Well, wait, you haven't seen anything yet. Check out this last example. If we go to a time where the prevalence was very low, let's take, let's see, I think I chose the 20th, yeah, June 20th, where there were 80.93K, meaning 80,930 cases ending that week. Divide that by the population of the United States at the time, and we find that the prevalence was 0.024%. 0.024%. Oh my gosh, look at that. Now we're finding that out of every 100 people at the time using that test with these sensitivity and specificity parameters, for every 100 people who tested positive, 98 of them didn't have the virus. Only 2 of them did. When you think about the importance of these numbers in determining policy, public health policy, and so on, I'm just surprised that this is not more well known. I've known about it for many years. I used to teach this as well, but I don't think generally people do know about this. I would expect, though, that the virologists and doctors and epidemiologists would have knowledge of this, of course. All right, so now let's do the math. One more thing. Before I do the math, I want to tell you that this is paradoxical in the sense that we only saw a 1% false positive rate given the specificity of 99%, and yet that translated somehow into an almost 98%, I'll call it true false positive rate. It's an odd way to say it, but the rate in the actual population of people who were uninfected, but in fact really received a positive test result. So it's kind of a paradox, and for that reason it's well known as the false positive paradox. You can Google it, or the paradox of the false positive, something like that. And that's why I entitled this video, The False Positive Paradox. But I also added the subtitle, The Fallacy of Base Rate Neglect. And let me just quickly explain. When we don't know the base rate of the virus in the population, if we don't know the prevalence, then we're kind of back to the situation where I asked you the question. And that is, if you don't have any other information but except for sensitivity and specificity, you draw some wrong conclusions often. That's the fallacy, because you're neglecting the base rate, that is the virus prevalence. Okay, now, how does the math work? Well, here's how it works, and I'll just use these numbers to tell you. If we take a population of 100,000, and that can actually be any number whatsoever, it's all proportional, but 100,000 is a nice, easy number to work with, we can then fill in boxes that tell us how many people have the virus, how many people don't have the virus, And of those, how many test positive? To find out how many people have the virus, we just go to the virus prevalence, multiply it by the population, and we see that there are 24 people in the 100,000 who would have the virus at this particular prevalence rate. And then over here, how many don't? Well, that's just the remaining 99,976 people out of the 100,000. Simply subtract. Now, this next row is about, of these, who's going to test positive? How many people? Well, if it were 100% sensitive, then that would be a 24, because all 100% of 24 is 24. But it's only 93%, 93.3% sensitive, so 93.3% of these people who actually are infected will test positive for it, and that's 22 rounded to the nearest person. Finally, we have this box. Of the 99,976 people who are not infected, how many will test positive? Well, according to this, 1% of them will. That's the complement of the specificity, 1%. And 1% of all these people is 1,000. It's actually 999.76, but rounded to the nearest whole person would be 1,000. Now, if you're interested in knowing what are the chances that you fall into this group, this little box, we just need to know, well, what fraction is 1,000 of the entire number of people who tested positive? Down here, what is 1,000 divided by 1,022? And that answer is 97.8. It's actually a relatively easy math problem, and it's all math. So if you dispute any of these figures, I would love to see what your reasons are in the comments. The one thing I can think of is that I'm calculating the virus prevalence incorrectly. And of course, I've already admitted to that. I don't know that anybody knows how prevalent the virus really is. But even still, changing this won't change that too much. Well, it certainly does, of course. As we increase the prevalence, this number will decrease. The specificity, that's the biggie. If we increase the specificity, then this number is going to drop because that will reduce the false positive rate. So let's try this. Let's suppose I went from 99.0 to 99.9. Well, can you believe that? It only dropped it down by about 10 percentage points or so. Well, no, about 17 percentage points. The only way it's going to drop to 0, in fact, is if I make the specificity 100%. And now there is no chance that your positive test result is a false positive. If the specificity is 100%, a positive is a positive. So if you can, you want to find a test that has 100% specificity. But as we saw on that list, this list here, many of them are not. Okay, I think I will close for now. I really appreciate your attention. If you have any comments to make, please leave them in the comments below. I'd love to get your feedback. And I appreciate you listening. Thank you so much. Until next time. Bye-bye.